Hello students. In this video lecture we are going to discuss about the implementation of AVL search tree with the necessary algorithms. The two major operations that have to be performed on an AVL tree is the insert operation and the delete operation. So we will discuss about the algorithms that are implemented for the insert and delete in a AVL tree. Similarly, we may also want to perform search and retrieval from the AVL tree, but for these operations we don't have to write new algorithms. We can just reuse the binary search or binary search tree algorithms which are for designed for search and retrieval, because AVL tree is basically a binary search tree, so we don't need to develop any new algorithm for these two operations. And among the traversal techniques, in order, pre-order and post-order, in order is commonly preferred for AVL tree because it's a binary search tree. So you know that in order traversal is the one that visits the node in the ascending order. So in order traversal is preferred when you want to traverse in a AVL tree. So unlike the search and retrieval, for which we don't need any new algorithms, but for insert and deletion, we have to do some additional modification into the algorithms. We can't just reuse the binary search tree insert and delete in the AVL tree, because it has an additional requirement that after performing an insert or deletion, the tree has to be balanced. So we have to add the module for balancing the AVL tree after any insert or deletion. Now insert procedure. So just like the binary search tree, whenever you want to insert a new node into the AVL tree, it has to be always done at the leaf node level. So we must locate a particular leaf node which is based on the value we want to insert, and then we have to insert the new value as a leaf node under the parent node. So any insert is always happening at the leaf level, and in order to find the appropriate leaf node, and we have to follow the path. So just like we did in the binary search tree, we have to start from the root. We have to compare the value of the root with the value we want to insert, and if it is if the root is larger than the value we want to insert, then we must move in the left subtree. That means that the new value is smaller than the root, so it has to be positioned somewhere in the left subtree. Whereas if the root value is smaller than the new value, then the new value has to be placed somewhere in the right subtree. So we have to traverse towards the right subtree. So in that way we have to keep progressing from node to node. Either sometimes we may have to take left turns, sometimes we may have to go in the right subtree. So finally we will be reaching a leaf node where the new node has to be inserted either as its left child or as right child. So this is step 1. We have to locate the ideal position for the new node or the new data. Once it has been identified, then it is just a matter of connecting the new data with the parent node, either in the left as a left child or as a right child, depending upon its value. But it does not end with this step. That is where AVL tree differs from BST. So after we have inserted the new value, we have to do one more step for AVL tree, which is we have to check for balancing of the tree. So after a new node has been inserted into the AVL tree, it might have spoiled the balance factor of the tree, and so we have to check for that. We know that an AVL tree is basically a binary search tree with an additional requirement that it must be balanced. So the balancing is very crucial for keeping the tree as a AVL tree. So that has to be ensured. So whenever we find that after insertion the tree has lost its balance, then we must rebalance the tree. And one more point is that it's not necessary that every insert should result in balancing, because an insert will need a balancing only if it has caused out of balance. So we know that when I say that a tree is an AVL tree is a balanced tree, it means that the balance difference between left subtree and right subtree can be either 0, 1 or -1. So depending upon what is the current balancing factor, the insertion of the new node may either have resulted in out of balance, or it might have still remained in the balance only. For example, if the left subtree is having the balance factor of -1, then adding a new node will only make it 0, even balanced. So it's not going to cause it to be out of balance. So that has to be verified whether the insertion had caused the balancing to lose and the tree becomes out of balance. Then only we have to add the or run the module which is meant for balancing the tree again. So for example, when we add a node on the right branch of left high node, okay, so the meaning of left high node is that the tree is not even, whereas it is left high, which means the height of the right subtree is 1 less than the left. So that is the condition. In that case, if a new node is inserted in the left subtree or in the right subtree, it's not going to cause out of balance because it's only going to make them evenly balanced. So that has to be ensured and verified whether the condition of the tree right now is even balanced or left high or right high. Accordingly, it could result in out of balance or no out of balance. Okay, and on the other hand, whenever the tree is evenly balanced, definitely an insertion would result in out of balance, because evenly balanced means that 0 0. So both the left subtree and right subtree have the balance factor as 0. So inserting a new node at either side will definitely cause out of balance, and it has to be balanced. So once we identify that the tree has become out of balance, then we must follow the procedure we already had seen with the examples, which is rotating. So we must rotate the tree either to the left side or to the right side, depending upon which side is excess, and so it becomes balanced again. This is our algorithm for the AVL insert. So the first step is, if the tree is empty, which means that we are trying to insert the first node into the AVL tree or an empty tree which is currently empty. In that case, it is a simple process. We just insert the new data at the root. Next condition is, the tree is not empty but it contains some data already. Now in that case, we have to identify the correct location. So the location is determined based on, it's very much like the BST. So we have to compare the new data with the value of the root. If the new data is less than the root, then we know that the new data has to be placed in the left subtree. So this algorithm is recursively called following the left subtree of the root. So this will go on. Similarly, if the data to be inserted is greater than or equal to the root, then it has to be placed in the right subtree. So the same algorithm is now called passing the root, the right child or right subtree of the root data. So this is it will keep on going until it hit a leaf node. So this algorithm will proceed in sometimes it will be if condition will be true, sometimes else part will be true. So finally it will reach a particular leaf node under which the new node has to be inserted. So this is the algorithm which is making call to the and one more point to be noted is that if the tree is found to be left staller, that is it's having a left high, in that case inserting a new node in the left side will definitely make it left balance. It's not even balanced. So when we say that left subtree is taller, it means that it is left high and it is not even. So adding a new node will cause the tree to become out of balance. So we need one more algorithm to balance it again, which is called the left balance algorithm. We will see that algorithm next. And similarly, if the same situation happens in the right subtree, that is the right subtree is higher than the left subtree, then adding a new node into the left subtree will also make it out of balance. So for that we need another algorithm which is called right balance algorithm. So this will be called. Now this is the algorithm we have got for the left balance. So whenever inserting a new node into a already left high node subtree is done, in that case this algorithm has to be made use of to balance it again. And we know how to balance a tree. We know how to balance a AVL tree. Whenever it goes out of balance, there are four possibilities. One is it could be a left of left situation, or right of right situation, or left of right or right of left. So we have four conditions. First two conditions are simple conditions. Left of left means that there is a excess node in the left side. So the simple solution is rotate it towards the right side, so that the excess node transformed to the or moved towards the right side, and it becomes balanced again. Similarly, the right of right also is a simple solution, is to rotate it towards the left side. But when you encounter left of right, in that case you have to first make it left of left. So it has to be followed two steps. First you have to make it left of left, and then you have to apply the solution we have just mentioned about left of left. Similarly, if it is a right of left problem, then you have to first convert it into right of right and then solve it. So that is what is also being referred here. If left subtree is high, then simply rotate it right. So it is a case of left of left. But on the other hand, if it's a case of right of left, then two steps are required. First step is to convert it into left of left. So this is called, in order to make the problem into left of left problem, so you just rotate it towards left, and after that you have to rotate it towards the right. So these two steps will be needed. And the algorithm for right balance is not going to be discussed, but you can imagine that it will be very similar. So if you it's going to be like some changes will be there to be suitable for right of balance algorithm. So that need not be discussed separately. Now the rotate algorithms. So we have mentioned here that rotate left and rotate right needs to be done. Then how do you do it? For that we have got the algorithm. To rotate a node, we simply exchange the root at the appropriate subtree pointers. This we already had seen in the demonstrations in the previous video lecture, that how to rotate a subtree towards the other side. Whether we rotate the left subtree towards the right, or we rotate the right subtree towards the left, we have seen how it can be done. And that is basically done by changing the root of the node. So whichever node that is currently out of balance, the root will be either moved towards the left or moved towards the right, depending upon the direction of the rotation. So this is the algorithm which is doing the rotation. It is just just mentioning what is to be done. So if in the case of rotate right, exchange the left subtree with the right subtree of left subtree. So rotate right means that the node which is in the left subtree has to be moved towards the right side. That is when it becomes rotate right. Similarly, rotate left means that the current node which is in the right subtree becomes the root in the left subtree. So it gets moved towards the left side, and that is what is the idea behind rotate left. This is an example to understand it. For example, I have to rotate it right. So what do I mean by this is that 18 should become the root and 20 should become the child of the 18. That means that it will become like this. So 18 gets into the root position and 20 becomes the right child, and this is adoption. I already explained it adequately in the previous video lecture. So whenever we replace the root, whenever we make a new node as a root, the child of that node, excess child of that node, has to be adopted by the previous root node. So in this case 20 is the root node that is being replaced, and 18 is the one that is going to replace 20. So the right child of 19 will have to be connected to 20. That's what is done here. So that is what that is the idea behind the rotate algorithm. Now the insert algorithm is completed. So let me just summarize. Whenever we want to insert a new node, step 1 is we have to identify the correct position or location for that particular node. It is always to be inserted at the leaf only, and we have to follow the BST algorithm for that. So we have to compare the value with the new value with the root value, and we have to either move towards the left subtree or towards the right subtree until we reach the leaf node. And once that is done, we just have to connect the new data with the root, with the parent, or the what was a leaf node now becomes a parent of the new node. But after that we have to rebalance the tree if in case it has become out of balance. So for that we have discussed various algorithms. Now coming to the delete operation, it's also going to be very similar. Deletion could also cause a tree to become out of balance, just like insert has the possibility. So all deletions must take place at a leaf node only, and AVL tree deletion follows the basic logic of the binary search tree deletion with the addition of a large balancing the tree. As with the insert logic, the balancing occurs as we break out of the tree. So whenever we finish the deletion after the node has been deleted, then we have to check whether the tree continues to remain in balance or it has become out of balance, and accordingly we may have to run the algorithm for rebalancing, or we can simply leave the tree if it remains in balance. So this is the algorithm for the deletion of a node from a AVL tree. So the algorithm as usual starts with the first condition, that whether the tree is empty. If the tree is empty, then the deletion cannot be done. So it simply returns a null value. On the other hand, if the tree is not empty, then we have to identify the location of the node or the key to be deleted. So for that we will be following the typical binary search logic. We compare the root value with the value we want to delete, and it may be either in the left subtree or right subtree. If it is in the left subtree, that is if the new value to be deleted is less than the root, then it must be somewhere in the left subtree. If at all, if it is there in the tree, it must be only in the left subtree of the root. So the search is now directed towards the left subtree. So we make a recursive call to AVL delete, passing the value of the left subtree. And if you come to know that the tree is shorter, that is in the left subtree is shorter than the right subtree, then definitely deletion will result in out of balance. So in order to balance it again, we make a call to delete right balance algorithm. Similarly, if the previous condition is false, then this condition may be true, which is if delete key greater than root. That means the deletion node to be deleted is somewhere in the right subtree. So in that case, the search is now directed towards the right subtree, and once again we check whether the tree becomes shorter. If so, we make a call to a balance algorithm, but this time it is a delete left balance algorithm. If none of these two conditions are true, that is the value to be deleted is neither smaller than the root nor greater than the root, which means it is equal to the root, that means we have found the node to be deleted. So only thing is that whenever we want to delete a node from the binary search tree, we did that we have to check under which condition it falls. It is either a case that it has no children. it means it is a leaf node. So deletion of the leaf node is a very simple case. Or it has only a left child without any right child. Then that left child becomes the root after the deletion. Or it only contains a right child without any left child. Then the right child is placed into the root. Third possibility is that it has both a left child and a right child. In that case, we can do any one of these, that either we can choose the smallest value from the right child or right subtree and bring it into the root, or we can find the largest value from the left subtree and place it into the root. So we can follow any one of these approaches, and that is the formal way of deleting a node. That is what is actually mentioned here. So once we reach the actual node to be deleted, we check for under which condition it falls. If no right subtree, that means that it may or may not have a left subtree, but definitely it does not have any right subtree. Then we just return the left subtree, which is going to become the root. On the other hand, if it does not contain a left subtree, then it means it only has a right subtree. So the right subtree is returned so that it is placed into the root. So these two are simple conditions. Now the major condition is that it has a left child or left subtree as well as right subtree. So we have to follow these steps. Find the largest node on the left subtree and copy that into the root, and then you have to initiate the deletion. So this is the way we also discussed, we saw in the demo how we can delete it. This is an example to make it easier. Say for example, a node has been deleted here. So after that we have to balance it again. So that balancing happens by rotating towards left, rotate left, because the right is become excess. The height of the right is out of balance. So in order to it is a case of right of right. So we rotate it like this. So 18 becomes the root, 12 becomes the left child, and as usual 15 becomes the right child of 12. This is another case with a slight difference. So here we do the same here. So 18 becomes the root, 12 becomes the left child, and 20 remains the right child of 18. So these are examples. So these are the various algorithms we can use for implementing the AVL search tree for the insert and delete operations. Thank you.